So far, we have limited our discussion of joint distributions to discrete probability masses, but the exact same ideas hold for continuous variables. So instead of having a joint probability mass function for discrete variables, we would have a joint probability density function for continuous variables. All of the same ideas hold. For example, if I want the cumulative distribution of x and y, that would just be done by integrating up, so accumulating all of the probability density associated with x being less than some point little x and y up to some point little y. And then just as we would get probability density by looking at the rate of change of this cumulative function, I have the same idea for the joint distribution, except it's got to differentiate partially in both directions, in the x direction and the y direction. So all we need to do is we need to think of this in the same way as we thought about joint probability mass functions, that it's just this function that, again, rather than summing the probabilities, I would integrate the probability densities. And again, because the total probability has to, I was going to say sum to 1, but in this case it's an integrate to 1, but integrating over all of the values across both dimensions. And although I've done this for 2 variables, those could be triple, quadruple, or any number of integrals. The ideas of marginal and conditional distributions that we saw for discrete random variables, they have the exact analogies in the continuous equivalent. To get the marginal, I summed all of the probability masses. I summed over my uncertainty in whichever variable I wasn't interested in, and I do the same here with an integral. If I've got f of x and y, and I just want to marginally know f of x, if I don't care about y, I integrate out over all my uncertainty in y. And also the conditional density, again, would just be the joint density, f of xy, normalized by the marginal density, f of x, to get the conditional density of y given x. And although I've only presented that for the 2 variable case of a joint distribution of x and y, if I had 3 or more, the same analogies hold. So if we've got a joint distribution here of x and y, and they have joint density function, f of xy is 2x squared e to the xy, and that's valid for x and y being between 0 and 1 each, and there is no probability density associated outside that region. So I want the marginal density of x. I want to integrate over all y. So I write this down. Well, firstly, I can pull the 2x out the front of the integral because I'm integrating with respect to y, and 2x is effectively constant with respect to y here. And I'm still left with an integral of e to the xy with respect to y over all y. But the only non-zero values of probability density are when y is between 0 and 1, so I can just integrate between 0 and 1. The integral of e to the xy with respect to y is e to the xy over x. Evaluate that between 0 and 1. I've still got the 2x squared outside, so I would get 2x squared multiplied by e to the x minus 1 over x. Can tidy that up a little bit. I want to verify that that is a valid density function. It's not instantly obvious that that integrates to 1, but it does. I won't talk you through the integration by parts, but maybe pause this and check that. Or maybe you could just believe me, one or the other, whichever you prefer. And when I perform the integral, I do indeed get 1. This also means that once I've got the marginal distribution, I can easily get the conditional distribution, because the marginal distribution is the denominator in the calculation for the conditional. So the conditional distribution of y given x is the joint distribution of x and y divided by the marginal distribution for x. And I could have done this, but worked out the marginal for y, in which case I'd have got the conditional the other way around. I can leave that for you to do if you wish. We say that 2 or more random variables are independent if and only if the joint distribution, the joint probability density function, or joint probability mass function factorizes into separate functions for each variable. Remember that we said that events were independent of each other if information about whether or not one event happened told us nothing about whether the other event would or wouldn't happen. So what we've got here is for the discrete case, if I have the joint distribution of x and y, then in every case, the joint probability mass, that xy equals mn, is the same as the marginal probability that x equals m, multiplied by the marginal probability that y equals n. And that has to be true for every m and every n. And then for the continuous case, it's the same idea, that I can write the joint density of x and y as a function of x multiplied by a function of y, where the function of x is the marginal density of x and the function of y is the marginal density of y. Usually this is quite easy to spot. There is sometimes a little bit of a trick case where the range of the random variable, the range of values for which the density is non-zero, depends on the other variable. So that actually is one that doesn't separate. So just keep an eye out for that. Not quite trick, but trap to avoid falling into. And associated with that, equivalent to the definition on dot point 2 and dot point 3, is that if they're independent, then the marginal and the conditional are the same. That f of x is the same as f of x given y, that y doesn't change our minds in any way about x.